Welcome back to AI, from Zero to Researcher. Over the last 4 episodes, we built a complete training pipeline. Models as parameterized functions, neurons and decision boundaries, hidden layers that reshape space, and backpropagation that tells every parameter how to change. You now know how a model learns. But here is the uncomfortable truth. Everything we measured so far was on the data the model already saw. Today, we ask the harder question: does the model actually work on new data? Episode 5 is about generalization, evaluation, and the mistakes that silently destroy real projects. If loss, gradients, or backpropagation still feel shaky, revisit episode 4 before continuing. Today, we are judging the outcome of that training process. I trained a model that gets 99% accuracy. Sounds amazing, right? But watch, I'll show you why that number might be completely worthless. Here is what happened. I fitted a curve to some data points. On those exact points, it was nearly perfect. Then I showed it 10 new points from the same source, and it was catastrophically wrong. The 99% accuracy was real. It just measured the wrong thing. This is the most underrated topic in machine learning. Flashy architectures get the headlines. Evaluation is what separates work that holds up from work that falls apart. Researchers who get this wrong waste months. Papers that get this wrong get retracted. And if you learn it now, you will have an advantage over people who skip straight to transformers. Let's start with the most fundamental idea in evaluation. You do not test a model on the data it trained on. Think about it this way. If a student memorizes the answer key to an exam, they will score 100%. That does not mean they understand the subject. The same logic applies to models. Training accuracy tells you how well the model fits the data it saw. It says nothing about new data. So we split our data into 3 parts. The training set is what the model learns from. Parameters get updated using this data. This is the answer key the student is allowed to study. The validation set is used during development. You check validation performance to decide things like, should I use a bigger model? Should I train longer? Should I change the learning rate? You never train on it, but you do peek at it repeatedly. The test set is locked away until the very end. You evaluate on it exactly once to get your final number. If you look at test performance during development and make decisions based on it, it stops being a genuine test. It becomes another validation set, and your final number becomes optimistically biased. Why 3 sets and not 2? Because the validation set gets used up by your decisions. Every time you check validation accuracy and change something, you are indirectly fitting to the validation data. The test set exists as an untouched safeguard. A quick note. When data is scarce, a technique called k-fold cross-validation lets you reuse data more efficiently. You split the data into k chunks, train on k1 of them, validate on the remaining one, and rotate. Every point gets to be in the validation set exactly once. We won't implement it today, but you will encounter it early in practice, and it fits right here conceptually. In episode 1, we said a researcher always specifies task, data, model, and metric. Now we add. A researcher also specifies how the data was split and what each split was used for. Without that, results are incomplete. Now we can define the central failure mode of machine learning. Overfitting. Overfitting happens when a model adapts too closely to the training data, including its noise, its quirks, its accidental patterns, and performs worse on new data as a result. The model is not learning the underlying structure. It is memorizing the specific examples. Here is the classic signal. Training loss keeps going down epoch after epoch, but validation loss drops for a while and then starts rising. That gap between training performance and validation performance is the overfitting gap. The opposite problem is underfitting. That is when the model is too simple, too small, or too poorly trained to capture even the real patterns. Both training and validation performance are bad. Think of it as a spectrum. On one end, the model is too dumb, it cannot represent the pattern. On the other end, the model is too flexible, it fits every detail, including the noise. The sweet spot is in between. Enough capacity to capture real structure, but not so much that it memorizes garbage. This trade-off between model complexity and generalization is called the bias-variance trade-off. A model with high bias is too rigid. A model with high variance is too sensitive to the specific training examples. We want a balance. This U-shaped curve is one of the most important diagrams in machine learning. Training error always goes down as you add complexity. A powerful enough model can memorize anything. But test error has a minimum. Past that point, every bit of added complexity hurts generalization. Your job as a researcher is to find that minimum. Remember the loft landscape from episode 4. Finding the bottom of that landscape on training data is necessary, but not sufficient. We need the model to find a region that also works on data it has never seen. Let's go back to that 99% accuracy claim from the hook. Here is one way it can be worthless. Suppose you are building a medical test for a rare disease that affects 1% of patients. A model that simply says, no disease, for every single patient gets 99% accuracy. It is completely useless. It misses every sick person, but the accuracy number looks great. This is why accuracy alone is often not enough. We need metrics that capture different kinds of mistakes. Now let's swap in a more realistic model and see what the confusion matrix tells us. Precision asks, of everything the model flagged as positive, how much was actually positive? In our example, that's 80%. Recall asks, of everything that was actually positive, how much did the model catch? That's also 80%. The formulas stay on screen if you want to verify the math. The point is what they measure. Precision catches false alarms, recall catches missed cases. There is usually a tension between the two. You can get perfect recall by flagging everything as positive, but your precision will be terrible. You can get perfect precision by only flagging cases you're extremely confident about, but you will miss many real positives. F1 score is one way to balance them. It is the harmonic mean of precision and recall. It penalizes you if either one is low. The bigger lesson, your metric should match your actual goal. In a spam filter, maybe a few false positives are acceptable. In cancer screening, missing a real case is far worse than a false alarm. The choice of metric is a design decision, not an afterthought. Back in episode 1, we said every ML system has 4 components: task, data, model, objective. Now you can see why metric choice is part of the objective. It defines what good means. Before we talk about what can go wrong with evaluation, let's talk about what can go wrong with the data itself. Because there is a principle that overrides everything else in machine learning: garbage in, garbage out. No model, no optimizer, no architecture can rescue you from bad data. If your inputs are noisy, mislabeled, or biased, the model will learn noise, mislabels, and bias. Noisy labels are more common than people expect. In a dataset of 10,000 images labeled by crowd workers, maybe 3 to 5% of labels are simply wrong. A cat labeled dog, a benign tumor labeled malignant. The model dutifully tries to fit those wrong labels. On a small dataset, a few bad labels can distort the learned decision boundary. On a large dataset, the majority of correct labels tend to overwhelm the noise, but the wrong labels still waste capacity and can create subtle failure modes. Class imbalance connects directly to the 99% accuracy trap we just discussed. If 95% of your data is Class A and 5% is Class B, a model can get high accuracy by ignoring Class B entirely. But imbalance is not just an evaluation problem, it is a training problem. The model receives far more gradient signal from the majority class, so it learns that class better. Techniques like oversampling the minority class, undersampling the majority, or weighting the loss function can help, but none is a universal fix. Recognizing the imbalance is the first step. Data bias is the most insidious form of data quality failure. If your training data does not represent the real-world distribution you care about, the model will perform well on data that looks like the training set and fail on everything else. A facial recognition system trained mostly on light-skinned faces will perform worse on dark-skinned faces. Not because the model is malicious, but because it never had enough examples to learn those features well. This is a data problem, not a model problem. The model learned exactly what the data taught it. Feature engineering is the practice of transforming raw inputs into features that are more useful for the model. Normalizing values to similar scales, encoding categorical variables as numbers, creating new features from combinations of existing ones. In classical machine learning, feature engineering was the most important step, often more important than model choice. Deep learning reduced its importance because neural networks learn their own features, Episode 3's representation learning. But it has not disappeared. Pre-processing choices like normalization still matter, and in domains with limited data or structured inputs, tabular data, time series, good feature engineering can outperform a deeper model. The research habit here. Before blaming your model, audit your data. Check for label errors, check for class imbalance, check whether your training data represents the distribution you care about, and document your pre-processing choices. The most common failure in applied ML is not a bad model. It is bad data. Now for the silent killer, data leakage. Data leakage happens when information from outside the proper training setup sneaks into the model or the evaluation. It makes results look better than they truly are, sometimes dramatically better. Here are 3 common ways it happens. Duplicate contamination. The same example appears in both training and test sets. The model is literally being tested on data it memorized. This is more common than you think, especially with large scraped datasets. Feature leakage. A feature in your input accidentally encodes the answer. For example, if a hospital dataset includes a column for treatment received and you are trying to predict whether a patient has a disease, the treatment column reveals the diagnosis before the model even needs to learn anything useful. Pre-processing leakage. You compute statistics like the mean or standard deviation from the entire dataset before splitting. Now your training data has been influenced by test data values. The normalization knows things about the test set that it should not. Data leakage has caused real papers to be retracted. It has caused real products to fail in deployment. The insidious part is that everything looks fine during development. Your metrics are great, your plots look clean. The problem only shows up when you deploy the model on genuinely new data and performance collapses. This is why we are going to deliberately cause leakage in our code demo, so you can see exactly what it looks like and how to catch it. Let's make overfitting visible. We will fit polynomials to data and watch what happens. Look at these 3 plots. On the left, a straight line. It captures the upward trend but misses some curvature. In the middle, a gentle cubic curve, a slightly better fit, nothing dramatic. And on the right, EOS. The degree 9 polynomial threads through every single training point, but between them, it swings wildly up and down. It is fitting the noise, not the pattern. Training error for degree 9 is essentially 0. The polynomial passes perfectly through every training point. But test error explodes to 2.92, nearly 40 times worse than degree 1. The model memorized the training data, including the noise, and produces nonsense everywhere else. Degree 1, a simple line, has higher training error but almost the same test error. It captured the real pattern, a roughly linear trend, without memorizing the noise. This is the bias-variance tradeoff in action. The degree 9 polynomial has the capacity to fit anything, so it fits everything, including the garbage. The degree 1 model is constrained, so it can only capture broad structure, which is exactly what generalizes. In episode 3, we talked about model capacity, how complex a function the model can represent. Now you see why more capacity is not always better. A model needs enough capacity to capture the real pattern, but constraints that prevent it from memorizing noise. In episode 6, we will learn specific techniques, dropout, weight decay, early stopping, that provide those constraints. They are called regularization. Now, let's deliberately cause data leakage and see what happens. The leaked model looks dramatically better, over 6 times lower test error. But that number is a lie. 10 of the 20 test points were already in the training set. The model is being graded on questions it already saw the answers to. If you deployed this model on genuinely new data, the real performance would be closer to the clean version, or worse. This is how real papers get retracted. This is how real products fail after launch. Everything in development looked great. The leakage was invisible unless you carefully audited the data pipeline. The fix is simple, in principle. Split your data before any processing, any feature engineering, any normalization. Never let test data influence any step of training. In practice, this requires discipline, especially in complex pipelines where data flows through many pre-processing stages. Let's compress what we covered. Data splits, training for learning, validation for decisions, test for final evaluation. 3 sets, 3 purposes, no mixing. Overfitting. The model memorizes training data instead of learning generalizable patterns. Watch for the gap between training and validation performance. Underfitting. The model is too simple or poorly trained to capture even the real patterns. Metrics. Accuracy is not always enough. Precision, recall, and F1 capture different kinds of errors. Choose the metric that matches your actual goal. Data leakage. When test information contaminates training, scores look artificially good. Split first, process second, and audit your pipeline. Bias. Variance trade-off. Too rigid means you miss the pattern. Too flexible means you memorize noise. The goal is the sweet spot. If this episode felt more methodological than the last 4, good. Evaluation is where serious machine learning separates from guesswork. A model is only as trustworthy as the evaluation that measures it. Treat evaluation design as part of the method, not as bookkeeping. We have now reached an interesting crossroads. We know how to build models, episodes 2 and 3, how to train them, episode 4, and how to evaluate whether they actually work today. The missing piece is practical. How do we train models that generalize well in the first place? In episode 6, we tackle optimization and regularization. You will see why mini-batch SGD beats full-batch gradient descent. You will see Adam, the optimizer behind most modern models. And you'll see the techniques that directly fight overfitting. Weight decay, dropout, early stopping, and data augmentation. These are the tools that bridge the gap between low training loss and works on new data. Here is a question to carry forward. In today's code demo, the degree 9 polynomial overfit badly. What if, instead of choosing a simpler model, we kept the complex model but added a penalty for having large parameter values? Would that force it to use its flexibility wisely? That idea, penalizing complexity while allowing capacity, is the core of regularization, and it is where we pick up next time.